My name is Adam Kowalski from the University of Washington. My thesis advisor is Suzanne Hull. And my thesis is on the white light optical and near UV continuum emission in M-dwarf flares. In the background is the ARC 3.5 meter telescope at the Apache Point Observatory, which is the main telescope I use to get flare spectrum. So it's a well-established property of the white light continuum in M-dwarf flares that multicolor photometry exhibits the spectral shape of a hot black body, about 8,000 to 10,000 Kelvin. Here are 4 time slices during a large flare on the M-dwarf AD LEO, showing you the broadband far UV, near UV, U, V, V, and R photometry, and the vested black body here in the solid line. Radiative hydrodynamic models show something very different. Allred et al., 2006, simulated flares on M-dwarfs using the 1D radiative hydrodynamic code radian. And here's the predicted white light continuum, with the dominant feature being a very prominent Balmer continuum in emission, and a sharp discontinuity at the Balmer show. So this Balmer continuum emission comes from the heated chromosphere, shines onto the photosphere and heats that up, generating a lot of the optical emission you see. There's also some partial continuum in here too. So my thesis objectives: to obtain high cadence flare spectra during M-dwarf flares and characterize the continuum components on short time scales. Second objective is to determine how these continuum properties relate to the light curve shapes you see in broadband photometry, so the light curve evolution of the U-band. Third is an overarching question, which is to determine how and where in the atmosphere this hot black body is produced. And that's primarily a modeling question. So what I've done is I used the 3.5 meter in the DIS spectrograph to obtain low resolution optical flare spectra, many per night, and also simultaneous broadband photometry from the same site. In the end, we have a sample of about 20 flares for a detailed line and continuum analysis. So the largest flare in the sample has acquired a name, the mega flare, and I show the U-band light curve right here. It reached almost 6 magnitudes at the peak, and a very elevated and extended decay. These vertical lines indicate the time window within which we had spectral observations. And within the decay, there are several secondary flares occurring. The continuum analysis for the decay phase of this flare is as follows. The flare emission is shown in black here, with the quiescent emission shown in purple subtracted out. It features greatly enhanced Balmer lines, and also a continuum rising into the near ultraviolet. We find evidence for a hot black body that dominates the emission longward of 4,000 angstroms, and the black body is shown in red here. Above the black body, at the bluest wavelengths, there's excess emission. So we subtract the black body from the black, and we get the black spectrum in the bottom panel here. We take the Allred et al. Balmer continuum model here and overplot it in red, and find that the shape matches the shape of the excess flare emission. And so the second component is a Balmer continuum at blue wavelengths. We derive area coverages of each of these components. We find that the black body is coming from a compact region, emitting from about 0.2% of the surface area of the star. The Balmer continuum emitting region is much more extended, coming from about 10 times larger area in the black body. So you'll notice here that there's a sharp discontinuity in the model, but we don't see that in the flare spectra. We're working on this and with the models, and it may be due to the blending of the higher order hydrogen lines at the Balmer limit. So recall there were several secondary flares during our spectral observations. Here's one such flare, the U-band photometry, color-coded to the corresponding spectra. So before the secondary flare, in black, there are 2 clear continuum components, the hot black body, here a PowerPoint representation, and then excess continuum emission, the Balmer continuum. As you go up the rise, the continuum becomes entirely black body dominated, and the Balmer continuum seemingly disappears. So here are the actual Planck function fits, 10,000 Kelvin to 15,000 Kelvin. To explain this, I'm going to subtract the black spectrum from the spectrum about halfway up the rise to isolate the newly formed flare emission, which is shown in black here, and shows many similarities to the spectrum of a hot star, with the Balmer continuum and Balmer lines in absorption, and a steeply rising spectrum in the optical. I'll overplot Vega to show you the remarkable similarities. Okay, so I'm going to now reconstruct a story of the decay phase of the megaflare. So, contributing to the decay emission is a very bright Balmer continuum, perhaps triggered at the initial flare peak up here. This is extended, comes from a large area, and so it may resemble the H-alpha ribbons that are observed in the sun here. Also contributing to the decay is a black body component. The area is much smaller, and so maybe it resembles the white light kernels seen on the sun and newly reconnected magnetic loops. When there's a secondary flare, a new kernel forms, also very small, and that emits a hot star spectrum. Now this hot star spectrum is certainly not predicted by the radiative hydrodynamic models. So to begin to understand it, we're going to model it phenomenologically. So we take the quiescent atmosphere of an M-dwarf, here temperature versus column mass, here's the corona and photosphere, and we put two Gaussian temperature bumps at or below the temperature minimum region, with peak temperatures between 10 and 20,000 Kelvin. We use the static NLTE code RH to calculate the spectra, and it gives us exactly what we need. A Balmer continuum and Balmer lines in absorption and a steeply rising continuum here in the optical. So combining all the continuum components. So the black spectrum here is the flare emission from right before the secondary rise, and the gray is the flare emission from halfway up the secondary rise. This is the Radian Balmer continuum model with the back warming and Paschen continuum here. We add on the first hotspot with a 10 times smaller area than the Balmer emitting region, which is what we initially observed, and we get the blue, which nicely represents the underlying continuum of wavelengths. Halfway up the rise, we add on the second hotter hotspot with the smaller area coverage still, and we get the red. So an important point to notice is that as you add on the hotspots, the Balmer continuum starts out large, gets smaller, and even smaller, which is what we observed. Okay, so here are some new results. We also have red spectra for all the flares. And here is the red flare emission from the decay phase of the megaflare. It features the helium and sodium lines, H-alpha, and calcium-2 infrared triplet. Here's the extension of a hot black body fit to the blue wavelengths. You can see there's clearly excess emission here in the red. We overplot the Allred et al. Radian model in red, which is the same spectrum that has been giving us the Balmer continuum. And it does a really nice job at getting the shape and amount here. I just want to remind you that the Radian models predict that this emission is from a Paschen continuum, you can see here the Paschen jump, and from increased photospheric emission generated by chromospheric backwarming. So excess red emission has been seen in broadband photometry of flares before. Here are 4 time slices that I showed at the beginning of the talk. In the late decay phase, the R band is elevated above the black body. And so maybe backwarming models can help us understand the late phase optical emission during flares. So I asked, what could be better than a megaflare? The only answer is 20 flares occurring on a variety of stars with a variety of peak amplitudes, total energies, light curve shapes, and with spectral coverage through nearly the entire evolution. Here I show U-band light curves of 9 of the flares in our sample, which will soon be submitted to FJ supplements. So just a quick peek at the 2-component analysis. Here are peak and gradual phase spectra from 2 very energetic flares, one with a large peak and one with a small peak. And you can see that the 2 continuum components have various contributions to the total continuum emission during the different phases of the flares and between the different flares. Okay, so we have a lot of information on the emission line evolution throughout all of our flares. And the emission lines are important because they give you constraints on heating at different layers in the atmosphere. Also, by comparing the evolution in the emission lines to the evolution in the continuum, you can start to understand the origin of the continuum. So here's a very typical looking flare. This is a broadband photometry G-band on 80 Leo here. This is the peak flare spectrum and the quiescent shown right here, and the hot black body present on the continuum there. So the models must reproduce three things. The first being the shape of this hot black body and the amount of Balmer continuum relative to the black body. They must reproduce the energy budget, that is the ratio of the total emission in the lines compared to the total emission in the continuum. So how important is the continuum? And they must reproduce the overall evolution of the various spectral components. So the various spectral components are shown in this panel here, normalized to the peak. The black body, shown in red, is very fast, exploding and then decaying very quickly. The Balmer continuum rises quickly and decays much more slowly, very similar to the H gamma. And so you can conclude that the Balmer continuum H gamma are coming from similar mechanisms, similar places in the atmosphere. Okay, so putting these are most of the flares on the same plot, just ordering them by the peak H gamma luminosity here. On the y-axis is the peak black body luminosity at 4170 and the peak Balmer continuum luminosity in the asterisks. And for the black body at peak, there are maybe two distributions here, one here and one here, with some in between, such that some flares emit brighter Balmer continuum at the peak than the black body, and some flares emit brighter black body than the continuum. When you consider the total energy emitted in both spectral components, they start to fall on two ordered distributions over 4 orders of magnitude. So here's the black body total energy and the Balmer continuum total energy. So I'm curious if solar flares show this same type of behavior between the peak emission and the total integrated emission. And because we have such great information about the spatial resolution of solar flares, how that can inform understanding of stellar flares. So here are two movies of two flares from the Solar Dynamics Observatory in the helium-2 line. There we go. Okay, the one on the left is slowly evolving. You can see the loops sequentially light up and many other things going on. And the one on the right is very quickly evolving, and all the action is happening in a very concentrated region. So I took the EVE spectra and synthesized an EUVE DS filter. And here are the light curves of the two flares. This is the one on the left, the slow one, and the one on the right, the really fast one. They differ in their peak magnitudes, peak flux is by a factor of 3, but the energy is actually very comparable, the total energy. And so maybe the spatial evolution is an important contribution to the different behaviors in the black body that we see in stellar flares. Okay, so some really exciting current projects that are going on. We are trying to get white light flare spectra of kernels on the sun. Here are white light kernels in the G-band, and we observed a C-class flare in August. And the spectra have the same wavelength coverage and a little better resolution than the stellar flare spectra that we have. Several very exciting stellar flare projects going on. Here's one of them with Kepler, measuring very precisely the energetics and flare frequencies, the flare rates of white light flares on M dwarfs. Here's 1 month of a very active M dwarf showing you all the flares on top of the rotational modulation. So here's the summary slide. I'm just going to put it up, and I wanted to focus on this last point here. We're really excited because we fired up Radian again, and in collaboration with Mats Carlson, who wrote Radian, we're trying to reproduce this hot black body. And we're trying to reproduce the evolution of the various spectral components. We want to see if we can get the hot black body, once we have it, to be very fastly evolving, and the Balmer continuum to stick around for a longer time. So thanks for your time, and here are my collaborators. Much thanks to all of them, and to my thesis advisor. And yeah, I'd love to answer your questions. Thank you.